10.4 Acid-base equilibrium. You'll notice here we have some hikers hiking on a mountain. You kind of wonder, what does that have to do with acids and bases? Maybe you already know that you produce lactic acid when you're exercising a lot. But anyway, we'll look in this section and realize the importance that equilibrium has to do with how our body maintains its oxygen level. Our learning goal is to use the concept of reversible reactions to explain acid-base equilibrium, use Le Chatelier's principle to determine the effect on concentration equilibriums when the reaction conditions change. So in an equilibrium reaction, two reactions are taking place. A reversible reaction proceeds forward in both forward and reverse directions. So we had this reaction earlier that had equilibrium arrows, but now if we take we take that equation and separate it into the forward reaction, which produces our fluoride ion and a hydronium ion, and then if we take these products and go this way and write the reverse reaction this way, you will see we have two reactions going on, and they go on and they are in equilibrium. Well, let's see. Now, then equilibrium is reached when there's no further changes in the concentrations of reactants and products. Notice they said no further changes in the concentrations. It doesn't mean the reaction stops. It's just that the concentration doesn't change. So the rate of the forward reaction is equal to the rate of the reverse reaction. So what that really is meaning is that the amount of these that are dissociated to form these is equal to the amount of these products that are recombining to form our original reactants. So let's see. Press pause and see if you can fill in these blanks. So before the equilibrium is reached, in other words, when the reaction is just starting, the concentration of the reactants and products do change because you have more reactants than products. So you're trying to reach that equilibrium. So some of the reactants are being made into products. Now initially, reactants have a rate of reaction faster than the rate of reaction of the products, meaning you got to get more products first before you can have that equilibrium. But at equilibrium, the rate of the forward reaction is then equal to the rate of the reverse reaction. And at equilibrium, the concentration of the reactant and the products do not change. The concentrations do not change. Well, here's where they do change. If a stress is put on them, if something changes, and let's learn about that something. And it's this wonderful principle called Le Chatelier's principle. When we alter the concentration of a reactant or product of a system at equilibrium, the rates of the forward and reverse reactions will no longer be equal. Why? Because a stress is placed on the equilibrium. And then we'll explain that. This, Le Chatelier's principle states that when the equilibrium is disturbed, the rates of the forward and reverse reactions change to relieve that stress and reestablish equilibrium. So let's see what that really means. Okay, they're using this visualization of two water tanks connected here. And they're showing that at equilibrium, these water levels are equal. Well, that's a good visualization. It doesn't mean that the concentrations, if we're thinking about a reaction, are equal. It just means that the rates are equal. All right. Now, if we were to put water in to this side, if there was an opening here and we poured water into tank A, well, we know that the water's not just going to stay here. It has a way to equalize. And so the rate of it going into here will increase until it levels out. All right. So let's do this chemically wise. If we have this equation, if I add more HF, like putting more water in this particular tank, what happens? Oh, the reaction is going to go forward more and produce more of this. Now let's see what that really means. When it does, it's going to produce more of the hydronium ion concentration, which is the strong acid. Le Chatelier's principle states that adding more reactant causes the equilibrium to shift to the directions of the products. until the equilibrium is reestablished. Now, what if we had taken away some of this HF? And let's put your hand there and hide it. Well, then if you don't have enough there, this product side is going to react and produce more of it because it needs to establish the equilibrium. So if more of our products react and go to the left, and if this rate goes more, then that actually means that this hydronium ion concentration, i.e. acid, decreases. So your pH is going to decrease there. Now then, Le Chatelier's principle states that the stress of removing some of the reactant causes the system to shift in the direction of the reactants until equilibrium is reestablished. Well, if we were to add more of our fluoride ion, think about let's go back here, think about if we were to have added more water in this side, we would have known that, okay, the reaction going that way would increase. And so that's what's going to happen if we're going to add some more fluoride ion. It's going to make our reaction go this way. The reverse reaction is going to increase so that we produce more of this, which means our acid concentration decreases. So Le Chatelier's principle states that the addition of more product to the system causes the system to shift in the direction of the reactants. So let's see how this applies to, hiking on Mount Everest at 28,000 feet. Okay. So we have our oxygen. We have our hemoglobin that doesn't have oxygen. When we add oxygen to it, it is going to produce our oxyhemoglobin. Now, if our oxygen level is high, like you're breathing it and it's high in the alveoli of the lung, then you're going to get more of this product. When we increase this amount right here, shifts it here. Well, why do you need that? Well, you need that to supply your tissues and your muscles. But on the other hand, if you were to take this oxygen away, i.e. you're hiking up 28,000 feet, or actually, anytime you're above 18,000 feet, you're kind of in hypoxia conditions. But let's say that you don't have enough oxygen in your lungs. Then if you take away this oxygen here, that's going to force this oxyhemoglobin to shift to the left, which means it is going to take away the oxygen from your tissues to go back and release the oxygen from this. So at 18,000 feet, a person receives 29% less oxygen. There's not enough oxygen. Why is there not enough oxygen? Well, because there's just not enough oxygen in the air at that height. Now, hypoxia is characterized by increased respiratory rate, causing symptoms such as headache, decreased mental acuteness, fatigue, and decreased physical coordination. So we see that if there's less O2, if we remove it, i.e. there's less oxygen in the air, then oxygen will shift the system in the direction of the reactants to reestablish equilibrium. So the O2 from our oxyhemoglobin will decrease. Now then, another important reaction is our carbonic acid in our body and how it maintains the buffer solution in our system to help with when we eat or when we exercise. So let's just show this general idea here. Using Le Chatelier's principle, predict whether the system shifts in the following of products or reactants for each of the following. So we all know, after this few slides, that if we're going to add more of our carbonic acid, by adding more to this side, it's going to shift our reaction that way. Well, look at this. If it shifts our reaction that way, it's going to make our solution more acidic, the hydronium ion concentration. If, on the other hand, we are going to remove some of this bicarbonate ion, the HCO3 negative, if we remove it, it's going to shift our reaction again to the right, and again produce more acid. On the other hand, if we add some hydronium ion concentration, if we add some hydronium ion, some acid, it will shift our reaction to the left. Now, let's look at another example. Another good example of Le Chatelier's principle is our respiratory system. When our food is oxidized in the human body, when we eat, some of it is converted to CO2, which must be eliminated. You think, okay, so food is just, eliminated through our normal ways that you would think food would be eliminated, but it's also some of it is made into CO2. Well, this CO2, carbon dioxide, must also be eliminated. Excess carbon dioxide can be transported to the lungs through the bloodstream and then you can breathe it out. However, the amount that can be transported just by dissolving CO2 is only about 15% that must be eliminated. The rest has to be eliminated another way, and the way it's eliminated is in the form of the bicarbonate ion. So when carbon dioxide dissolves in our water, so when we eat, and some of the food that's oxidized is converted to CO2, it dissolves in water to form carbonic acid. Let's continue on. Now then, the carbonic acid is going to react with our hemoglobin that doesn't have the oxygen of the red blood cells, and when it does, it transfers the hydrogen ion from carbonic acid. So it's going to transfer a hydrogen ion to here, and in so doing, it makes our bicarbonate ion. Now then, this is transported, it doesn't just sit there. This goes to the lungs, and then the hemoglobin here, the hemoglobin that has the ion, is going to pick up oxygen from the lungs to make our ion here. Now this hemoglobin ion is more acidic, it's got an extra hydrogen with positive, and so because it's extra acidic, it's going to react with this bicarbonate ion to produce our hemoglobin plus carbon dioxide. Well, let's continue. Now let's look closer at this reaction. This is kind of our end result, that things are going to happen here to these two products. And let's look at these two products individually. If we look at the carbonic acid can dissociate, because it's in liquid, it can dissociate, and in so doing, it is going to release CO2. At that point, it releases the CO2 for you to breathe out through the lungs. And another item is water that you can also breathe out through your lungs, a little bit of moisture, but you end up peeing some out too, or sweating some out. That's another way you get that out. Now let's look at our oxygenated hemoglobin. Now our oxygenated hemoglobin is going to be carried back to the cells, and the oxygen is then released for use in the food metabolism, and guess what? This process starts over. So this whole process is brought about by a stress on one system, an increase of one thing. Now, on the other hand, this cycle could have been reversed depending on if we have increased oxygen or decreased oxygen. This actually, at this point, is actually tied in back to our reaction right here. This one right here, what we were talking about with breathing. Now, do you need to know all these different individual steps? No. But later on in the biochemistry, it's just amazing how Le Chatelier's principle applies to something so simple as eating.